All right, let's go ahead and jump in here. We're in our chemistry book, and if you see here on the left, we are in unit number 2, and we are in 2.4, the structure of the periodic table. Click that guy. And this chapter and the next chapter, we're going to be exploring the periodic table, um, what it is, how it's made, and the trends that are demonstrated on it. So if we go into our Explore page here, and let me just go ahead and change this to tablet mode, go back there. The essential question for Explore 1, how do scientists distinguish between metals, metalloids, and non-metals? Okay, so if you recall, if we went to our P table, you could see that there were the metals. You had the non-metals, you can see that, and then you had the metalloids, which were kind of like this jagged line in between, right? So how do scientists distinguish between those? Roman numeral 1. Let's actually first draw our lines, okay? Today's date is 11/1, and it is Wednesday, 11/1/23. We'll leave some room for any margin notes that you want to take. Our essential question: how do scientists distinguish between metals, metalloids, something halfway between metals and nonmetals, and of course, nonmetals? Okay, and Roman numeral 1, we start with the periodic table. Okay, so if you take a look at this first paragraph here, the periodic table includes information about all the elements that have been discovered, as well as the man-made ones, what they call the uranium transition elements, ones that we've made in the labs, right? And they say that elements was similar. If you've read this, and of course I encourage you to read this ahead. In fact, actually, I would suggest that let me backtrack a little bit here. And you're gonna hate me for this. Don't hate me for this. You know what I'm gonna ask. What do I already know? What I already know. Okay. Hit pause for just a second and write down what you know. Maybe you know a lot, maybe you don't know anything, and that's okay. Just write down what you know. Okay. After you've done that, now we can go ahead and write the periodic table. It can be organized in 2 ways. Elements with similar chemical and physical properties are placed together within groups, aka families, and these are the vertical columns, right? There are also patterns in the way elements appear within periods. The periods are your horizontal rows. We call them rows. And what do they tell us? They indicate the number of electron energy levels in an atom, right? So let's go ahead and write that down. We got groups, aka families. What are these? These are the vertical columns. The vertical columns. They give us information, a lot of different information actually, but so far you've learned that info such as the number of valence electrons, right? You guys have learned about that. Okay. And if we take a look over here on our periodic table, you've learned that the old naming style was we called our group 1 and 2 were actually called 1A and 2A, right? We're talking about the American nomenclature. This was a 3A, 4A, 5A, 6A, 7, sorry, 7, 7A, and this was 8A, right? So those told you the number of valence electrons, okay? And this especially works for the representative elements, which was 1 through 2A and 3A through 8A. If using the international, remember there's that new international naming. If you're using the international nomenclature, which was 1 through 18, then basically 1 through 2, columns 1 through 2 told you that you had 1 or 2 valence electrons, and 13 through 18, what did you have to do for these? Subtract 10 to get your valence number, right? Okay. I'm going to go ahead and just clear our screen over here. Now you also had, on the side here, you had these numbers. And these numbers told you a little bit about the number of energy levels. Okay, so if we come over here, you had your groups, which were your vertical columns, and you have your rows, what we call your periods. How many do you have? You have 1 through 7. And what does that tell you? It tells us info such as the number of energy levels. And if you recall, that would be your first quantum number. The first quantum number, right? So row 1 tells us that you're dealing with quantum number 1, n equals 1. Okay, this is your principal quantum number. Okay, and you can go all the way up to 7 on that. Okay, that's review. I know that's review. We've talked to you about this already. All right, moving on. Clear our screens. There are many versions of the periodic table that include slightly different information. So we've already shared with you the US version, right? You have your A group elements, which are your main group elements, also known as, often called your representative elements. And the B group elements are called your transition metals, okay? So that might be worth noting here. How do we want to say this? Let's go back up to the top here. it says that you had info such as the number of valence electrons works for the representative elements 1 through 2A, 3A through AA. Okay. Let's make a side note over here. Okay. This might be a good place to do this. What are we talking about here? We're going to look at this. If you take a look at this group here, numbers 3 through 12, we're talking about these guys, right? Then we call these your, what did your text say? We call these your B group or your transition metals, all right? So your B group elements are known as transition metals. And what are they? They are, just take a look again here. They're numbers 3 through 12, okay? Let's actually put that just down as group numbers. Group numbers 3 through 12, okay? And again, this is a little bit of heavy lifting. You have to learn this stuff, right? We don't expect you to get it all at once, but you got to hear it, and you don't want to shy away from it. You just got to accept it and try to learn it. Okay, now there was a newer version, a newer naming method. You guys saw the International Union of Pure and Applied Chemistry, IUPAC. I was trying to remember that in class. They number them 1 through 18. That's like the newer standard, okay? Okay, coming down to the next paragraph. In all versions of the table, elements are placed in the periodic table according to increase in atomic number or the number of protons. You guys told me that in class. The configuration of electrons in an atom can also be predicted using the periodic table. These details about the atomic structure, this is important. These details about atomic structure affect the chemical and physical properties of an element, okay? So I want you just to kind of make a note of that, okay? So what did they say? In general, your periodic table is divided into 3 broad categories. Okay. Let's go ahead and put this down as letter C, okay? Letter C. In general, there are 3 broad general categories. And again, if we come over here and look at our periodic table, what are those general categories? You have your metals, nonmetals, and in between are your metalloids. They have some characteristics of metals and some characteristics of nonmetals, okay? So let's go ahead and just delineate those. Let's just mark that down, okay? We got our, you have your metals. You have your metalloids and non-metals, okay? Now, I showed you a few videos in class, but make sure to refresh yourself if you need to. Watch these video segments. They're helpful, okay? This image here that we showed you in class kind of showed you the 3 different nomenclatures that are used. Okay. Now, this looks like an interesting thing here. This looks like they made a mistake in Discovery Education because here it is all over again, right? I just talked about your group and your periods. And I talked about the designations. So sometimes that happens, I've noticed. Okay, so we're just going to kind of skip through. There's a second video that I showed in class, the general characteristics, a little bit of additional information. And let's jump into, so what exactly are metals versus metalloids and nonmetals? Okay, so we're going to call this small a, and we'll talk first about metals. Consider the metals around you. Maybe you have a bicycle, it's made out of metal. It might be a light metal like aluminum. It might be a strong metal that's light like titanium. Perhaps it's a clunker of a bike, a heavy one made out of iron, or some kind of alloy, iron and carbon or something like that, right? So you can, a lot of different metals that we use in our life. So what are the metals? On the left-hand side of the periodic table, metals are primarily groups 1 through 12. Some elements in groups 13, 14, 15 are also metals. You've got an image here. Any of a group of elements found in the ground, such as gold, such as this gold, that conducts heat and electricity. So yes, that makes sense. Where do we find metals? We find them in Earth as ores, found in Earth in rock, right? And when we find those metals in rock, they are often called ore, found in Earth as ore. You can have iron ore, for example, and we have to separate the metal from the rock before we can do anything with that metal, right? Needs to be separated from rock initially, right? So what are some of the characteristics of metals? Once we've done that, once we've smelted it, you separated it, and you have a pure metal, what makes a metal a metal? Well, what does it say here? It conducts heat. Okay, so we got it conducts heat and electricity. So those are some qualities. So we're going to write these down. Characteristics. It might be a good way to go. Well, they are conductive. They conduct heat and electricity. That's why we use copper in our walls, right? We use the metal to conduct electricity. That's why you use metal pans to cook, because they conduct heat, right? Metals exhibit similar properties. What else can we say about them? They require a lot of heat to melt. They have high melting points. High melting points. Okay. Get them hot enough, and eventually they can go from a solid into a liquid. Get them even hotter, and you could potentially turn them into a gas, right? What else can we say here? We're going to talk about valence electrons here. But before we talk about these valence electron things, let's just continue with the properties. We have malleability and ductility. Okay. Malleability. You can take a hammer and shape your metal into different shapes, right? In the old days, they would do that with cars. Jewelers do that when they shape your jewelry. Ductility. You can take a cube of metal and you can draw it out into a long wire. It can be drawn. I'm not saying drawn like you draw a picture. I'm saying drawn like you stretch it out. Drawn into wire. Right? These are some of the characteristics. Don't they tend to also be shiny? They have luster. Shiny, what we call luster. They have luster to them. Okay. And all right, and I don't want to jump into nonmetals yet, but we just have talked about the characteristics of metals. So now let's backtrack a little bit because they were going to share with us this whole thing about valence electrons and these seas of electrons. What in the world are they talking about here? Okay. Valence electrons produce many of the familiar properties of metals. Most metals are quite reactive because they easily gain, lose, or share valence electrons. Okay, so maybe we should say these qualities. What qualities? These qualities, right, are due to the valence electrons. Remember we said Lewis's Lewis structures, he was interested in describing elements and representing their valence electrons because he realized that this is where the action happens. The outer shell, the highest energy level, if they're stable, they're not reactive. If they're unstable, meaning they don't have a full valence, then they will be reactive. And that's what this is. Metals are often reactive, okay? These qualities are due to the valence electrons. Why? Because they easily gain, lose, or share electrons. Okay, this is a pretty important thing here. And that has to do with valence electrons. Okay. In solid metals, the valence electrons are shared equally among positive metal ions. Okay, there's a fact. In solid metals, valence electrons are shared equally among positive metal ions. Okay. And we'll probably come back to that statement and consider it more. These electrons flow freely between the nuclei of the metal atoms. They form a sea of electrons and move easily through the outer shells of metallic atoms, which explains why metals are good conductors. Where am I at? I'm over here, and we're looking at this paragraph here right now. And this is kind of an interesting concept that you're going to see from time to time. Okay, so we're considering it right now. However, the attraction between the positive metal ions and the sea of electrons is strong. This explains why most metals have high melting points. Okay, so I think point number 2 here. A sea of electrons is formed between the nuclei of atoms and their valence electrons. Okay. Therefore, right, this little symbol here, therefore, this little symbol means therefore metals make good conductors. Okay, all right. However, the attraction between the positive metal ions and the sea of electrons is strong, and this explains why most metals have high melting points. But because attraction is strong, comma, metals have high melting points. They take a lot of heat to melt. All right, got it. More of that to come, okay? More of that to come. All right, we talked about this. Malleability is the ability of the element to be molded into another shape. We talked about that without breaking or cracking. Ductility. So here we are. We're talking about malleability. Ductility is the ability of an element to be pulled into a long, thin wire. Let's look at this red highlight. The sea of electrons can flow with metal ions when they move. As a result, the metal ions slide past each other without breaking the bonds that hold them together. Okay. That sea of electrons. You won't see it just in this text. You'll see it in different books, and they'll describe it the same way. And then you have this other quality, luster, refers to the shine, right? Most metals are shiny, right? Okay, got it. All right, let's move on to nonmetals, okay? This is going to be, metals was 1, C1. Now we're going to talk about, I better draw this line down here. And now we're talking about 2. This will be number 2. And we're talking about non-metals now. Non-metal elements are located on the upper right-hand side. You can see that here in this picture, right? These are your non-metals. Okay, if we take a look over here on our periodic table here, and I highlight, there's the non-metals over on the right-hand side. See that? The non-metals. And there's your reactive nonmetals, and you have your noble gas nonmetals. Okay. Atoms of most nonmetals tend to gain valence electrons during chemical reactions. That's actually an important point. Atoms of most nonmetals tend to gain valence electrons during chemical reactions. And it doesn't take a lot of, let me just show you for an example. Okay, if we take a look at, we won't look at any of our group 8A, okay, because these are your, let me clear my screen here. These guys are stable. These are your noble gases. So they're pretty non-reactive. Why? Because they have a full valence, right? They already have their 8 electrons in their outer shell. They're pretty happy, Okay, but these guys, let's take a look at something like your 7A group, i.e., if you have fluorine, fluorine has 1, 2, 3, 4, 5, 6, 7. It has one unpaired electron. It needs one electron to be stable. Chances are it will gain an electron. That's the easiest thing to do. Instead of giving up um, its valence electrons and lowering itself to a lower energy level to achieve stability, it's probably just easier for it to gain the one electron, right? If you take a look at, and that's for anything in the 7A group, chlorine as well. Chlorine, it's also in the 7A or group 17, so it has 1, 2, 3, 4, 5, 6, 7. It also has one lone electron. It's probably going to be easier for it to gain an electron to become stable, right? If you take a look at, say, carbon, let's just go all the way over to carbon over here, okay? Carbon has how many? It has 4. 1, 2, 3, 4. This is almost a coin toss here, but there's a good chance that carbon will also gain electrons to gain its full valence. If you take a look at something like oxygen, how many does it have? It's in group 6A or 16. 1, 2, 3, 4, 5, 6. All it needs is an electron and an electron, 2 more electrons, and it'll be full. So its chances are it's probably just going to gain 2 electrons. And that's what they mean. Most of them on the right hand tend to gain valence electrons. Okay. Nonmetals tend to have low melting points. Okay, that is a difference versus metals. Let's write that down. Okay. They tend to have not high melting points, low melting points. Okay. Therefore, they often exist as gases at room temperature. At room temperature. Okay. When solid, nonmetals often exhibit properties such as brittleness. They break easily. They are poor conductors, and they are not shiny. They are dull. Okay. So we're talking about qualities. They tend to have low melting points. What else do we want to say? They tend to be brittle. They are poor conductors. And they often look dull in color. Okay. The properties of nonmetals, we're looking at the next paragraph over here. The properties of nonmetals are also explained by attractions between valence electrons and the nuclei of atoms. Okay. Just like metals. Unlike metals, nonmetals hold their valence electrons tightly. Nonmetals share electrons between a few atoms to make molecules. However, the molecules do not share electrons with each other. They're held together by weaker forces, which is why nonmetals often have low melting and boiling points. Nonmetals are brittle. Okay, so what can we say about this here? Let's put this down here, okay? We're going to say 1 nonmetals hold their valence electrons tightly. Okay. And that might be a point of distinction versus metals. Okay, let's see here. Let's just kind of make sure we're being consistent here. This is a pretty long lecture. We'll put this thing here. And now let's talk about metalloids. Okay, this is the last thing we're trying to understand here. So we had 2 as nonmetals, and now we're moving into 3, the metalloids. Okay. There are only 7 elements that are considered metalloids. They appear in groups 13 through 16. They form a jagged line between the metals and the nonmetals. Here we go. Your metalloids. Right, so there's our metalloids, and they kind of form a jagged line. 1, 2, 3, 4, 5, 6, 7. You can see those all kind of in a light greenish blue color. There are 7 of them, 7 elements. Form a jagged line between metals and nonmetals. Okay. The metalloids exhibit properties of both metals and nonmetals. Have properties of both metals and nonmetals. Okay, so what are those properties? Okay, for example, solid at room temperature. Okay, they have luster, just like metal, right? But like nonmetals, they're brittle, or usually brittle, and they behave like nonmetals, which you could assume means that they're not conductive, right? Behave. And perhaps they maybe don't have as much malleability. Maybe they don't have as much ductility, right? The physical properties of metalloids are related to the attraction between valence electrons and nuclei, just like your nonmetals and your metals. So what is that? Metalloids hold on to their electrons more tightly than metals, but not as tightly as nonmetals. It's kind of like that Goldilocks and the Three Bears kind of story, right? So I guess we could say something like this. You could say, if you were to draw a line and you said you had metals, and over here you had non-metals, and in the middle you had your metalloids, we could say they hold them less tightly than non-metals, but they hold them less tightly. Let's see here. Metalloids hold on to their electrons more tightly than metals. Okay, so metalloids hold onto valence electrons more tightly than metals, but they hold them less tightly than nonmetals. Nonmetals hold valence electrons very tightly. And what can we say about the metals? Hold valence electrons, could we say loosely? Somewhat loosely? That's why they make good conductors, because of that sea of electrons, right? Okay. All right, let's see here. Yeah, under certain conditions, electrons can move between atoms, which is why metalloids typically act as a semiconductor. Okay, I really am going to encourage you guys to take some time and read these paragraphs here, okay? There's a lot of information here. And it's going to take some time for you to wrap your head around this, okay? Metalloids typically act as semiconductors. Why? Because electrons can move between atoms, which is why a metalloid acts as a semiconductor. And what is a semiconductor? They conduct heat and electricity more easily than nonmetal, but not as well as metal. And we use these a lot in your electronic devices, okay? So we're still talking about metalloids, and we're going to put this as letter B. Letter B. Metalloids act as semiconductors. Okay, and that kind of means that they act halfway between your metals and your non-metals. Metals are good conductors. Semiconductors are kind of good conductors. Non-metals are not good conductors, so they're in between, right? And semiconductors are used in electronics. So you would expect that your metalloids are going to show up in a lot of your electronic devices. Okay. And what do we have? Where we got a video exploring the nonmetals. We have a video that explores the metalloids. And that's about it. Alrighty. Well, let's have you do this. As always, I want you to take a moment to write yourself a summary sentence. Okay, I'm going to be looking for these. So let's just take a line, draw a line here. And we'll say summary sentence. And I'll be looking for this in your notes, okay? In a couple sentences, summarize what you just learned from this video lecture in your own words. Don't be easy on yourself. Don't write just, we talked about metals and non-metals and that was it. Try to be specific, focus on things that are difficult for you, and try to summarize those things so that those things stick in your head, okay? Alrighty, you have a great evening or day, and we'll talk to you soon. All right, bye-bye.